right, it looks like my screen is showing and I'm recording. All right, so next up, this is the bass assembler instructions. And we won't need to make a lot of changes to them. GitHub. So yeah, Peter Lemon N64. Peter Lemon has made, I don't know, probably hundreds of N64 assembly language programs, primarily with the intention of being able to test the accuracy of emulators. We saw an example of that in the first video. And just so much great code, great examples. I learned MIPS by reading his code. And so we're going to take a look at the initialize program. And this is the smallest N64 program that will work on an actual console. Emulators are not quite as critical, and we'll see that this little 4-line piece of code is actually the 3 lines of code are actually required for the N64's security, to make sure that it's an authorized game kind of a thing. But what we're going to cover, and I'm going to go through that here, is the keywords at the top. So I'm going to just I'm going to work with his on the one side and mine on the other. And I don't think it'll matter just a tiny little bit as we move on. So the first line here, and again, I'm going to focus on this block for now, up to about there, and just kind of explain what's going on with these. So these are the things that are specific to the bass assembler. Here, Arch refers to the architecture. In this case, I've specified the N64 CPU, which is the main MIPS processor. Other options for the CPU portion of this is RSP for the reality signal processor. It's another little MIPS core that's in the N64. The reality drawing processor, which handles the actual drawing instructions to draw triangles and rectangles and things on the screen. I think those are the 3 key pieces for the architecture on the right of the period. On the left, this is where it gets a little bit interesting, because this assembler was originally created to support the Super Nintendo, and that's where it started. And I believe it was ARM9 who added support for some of these other platforms, but I believe that it's now usable for Game Boy, Game Boy Advance, NES, and lots of other architectures. So any skills you learn relating directly to the bass assembler will apply to the other platforms, which is cool. So here, Endian, and our value, Endian is a keyword, and our value is MSB. So we don't hear so much about it anymore, but especially in the 90s, you had the endianness factor. So you had big endian and little endian. Intel is the little endian. MIPS is big endian. And so the alternative value here is LSB for least significant bit. You know, as long as you get the right bit endianness for your platform, for the most part, you can ignore it. And there's a lot of other resources that'll probably explain it better. Yeah, I'm going to leave it at that. There's some byte swapping and some other things that get weird with it. But N64, MSB, or big endian. So this output line. So this line is optional. The first two are required. Output, and what this refers to is the name of the ROM that is created. This way it can be different than the source file name. By default, it will take the source file name, but you can make it something else here. The other thing that's interesting here is this create. Oh, you know what? I almost forgot. All of this, the Bass assembler is actually fairly well documented. And the documentation is local, and it's available on the website. It's in the GitHub, but I don't think it's quite as... he doesn't have it set up on like a GitHub IO, so it's just an HTML file out there. So use the local version. So here, and first I'll point out, it's actually really long. This is a very full-featured assembler. We're going to cover macros and constants and defines and all kinds of other things that are available and possible. I'm not going to say we'll cover everything, but as it becomes relevant, we will use it. So lots of cool stuff here. So what we're looking at right now is the output keyword. And so here only... Okay. So there is not an alternate for create. It's either there or it's not. So create means that it's going to create a new ROM from scratch and just start laying out the bytes and instructions in the ROM file. If you exclude the create, it allows you to go into a modification mode, which is, it's a really cool feature. I haven't truly used it, but it allows you to create patches for a ROM. And there's another keyword in just a moment that we'll look at in regards to that. So kind of a neat feature. But for us, we'll be creating new ROMs every time. And once again, the name, I'm not sure how we'll use this. I kind of like putting it there, but we don't have to. All right, so next up is the fill command. And this seems like a pretty random value, but there is something to it. So I'll kind of show you the math that goes into this. The N64 has a 4 kilobyte header, and this contains it contains things like the ROM's name, a couple of configuration settings. There's a couple of technical bits to it. There's also some things like publisher codes that are put in there. Some other little data bits. But that's about 4K. And then when the N64 boots up, it actually copies the first megabyte of the game code from the cartridge into the console's RAM, starting at address 0 and up to the 1 megabyte mark. So what we get then is, here, let me switch this back. Let's see. So 4 times 1024, because this is all about, in decimal mode, 4 times 1024 is 4096 bytes. And I'm going to save that. And then I'm going to do this and say 1024 times 1024. And that is equal to, it's 1 megabyte in normal speak, but 1,048,576 bytes, and then we will add it to our memory value, and we will get our 1052672 value. So it's the 4K header, which is the technical bits, the ROM name, and we'll see this in just a moment. Then that's only the first 64 bytes. Then after that is boot code, which is specific to the cartridge, and we'll see those in just another couple lines here. But the number is not just randomly generated; it comes from somewhere, and so that's where it comes from. So I'm sorry. The reason that we would do this, and now we know the size and where that comes from. We want to make sure that the N64 is going to copy a full megabyte no matter what. And we would rather it not copy garbage. We don't know what's going to be there. And so by using this fill statement, we know that it's going to be zeros, that it's writing out to that first megabyte. If we're under a megabyte, we don't have to change this line if our game goes over that size. It'll just say, oh, you've already exceeded this value. I don't need to fill. And so that's good too. So this just makes sure that that memory gets zeroed and doesn't get really strange values that can cause problems. All right, next up is our origin statement. So I'm going to talk about origin and base a little bit together here. So origin refers to the position in the ROM file. And so this is the location in ROM. And so to give you an example, if I actually here, so I'm trying to think right there, just to give everybody a sense of what value this is. Okay, that's 1 megabyte. So I'm going to make that 2 megabytes. Here, CD. Okay. So we can see here, this is my old compile of this ROM at 1 megabyte. And if I look again, we can now see that it's over 2 megabytes. And because we told it that's we actually, so it's kind of like the fill statement. It's writing out zeros until it reaches this point, and then it will start to do this stuff. So it's just writing out the filler up to that point. I don't know that we'll mess too much with this. This is another one of those features that is very useful for the patch ability that's built into the assembler. So for the most part, our files will always have these zeros. And so here, I changed that, I saved it, I make it again, and we can see that I'm back to a megabyte, or our fill value in size, because our code is under that. We'll probably mess more with that later. I'm going to move on. Next is these include statements. So these are really similar to using statements or include in C. They're really similar. And so let's take a look at where these are pointing to. Lesson 2 is where my code is. Right there. That's the file that I'm editing. And we can see that those match up with the hint. So the line 12 here is saying go up one level and then back down into the lib folder, and you will find n64.inc. So I'm going to go ahead and open this up. And you can see here that this is a collection of constants. Here at the top, we have basically, instead of specifying just a number for our register number, we can use a little bit better name of, R for register and then the number. But down here just a little bit further, these are the more standard or traditional register names. And we'll cover what these are and why they are different. And this is more by convention than hard and fast rules as to how these are used. So don't get too hung up on them. In many cases, you're just fine using your numbered register value. And again, here's our floating point registers, kind of what we saw in the debugger. This just allows us to write code against them. Then here we've got some values for the memory map. And again, we'll cover this in more detail, but just the point is that this is a file that's a collection of constants. Down here, we actually do have some macros, and we'll cover these in more detail. But it's an include file. It's an extra source file. It allows us to use multiple source files to create our programs by using the include statement. Okay, so we can see by the lack of a path statement here that is pointed to n64 header.asm, and that is actually in the same folder as our lesson02.asm. So here is what that looks like. Really basic. This is kind of those values that I talked about. These first four values, this is the second one is formatted a little differently and therefore colored differently. It's just an example. These are they're all hexadecimal representations of a byte. So this is the same as that. And I can come here and do that. And it didn't change anything except what it looks like to me as a developer. I do like consistency, but I wanted to point that out, that you can use the $sign and the 0x interchangeably. All right. So these first four values, they have a more technical usage, but most people use these to identify the endianness of a ROM, as far as what sequence the bytes are in. And again, we're not too worried about that at this point, so if you want to research that topic on the side, by all means. So then we have a clock rate value, another technical value that the N64 uses when booting the ROMs. This start is kind of interesting. It actually turns around and points to this label, which is where our code will actually start running. So that's in the header, and so the N64 looks here and says, oh, that's where I need to jump in order to start executing code. So kind of cool. This value, I don't know. I think it's just another technical value. I'm going to leave that alone. So this, I'm going to kind of back up for a moment and point out that some of these are DB, as in boy, and some of these are DW. And the DW is for word, the B is for byte. So it's a data byte or a data word, and that's all I've got here. Okay. There are also options for DH, I believe, is a data half word, and DD is a data double. So those are a single byte. A word on N64 is 32 bits. And so the reason to point that out is this gets a little bit interesting here, because this says DB, but we look here and we actually see 4 characters. So these are ASCII. This is a cool trick. That's the shortest version. But CRC1 and CRC2 are going to get replaced. These are placeholder values so that you know where they're going to go. When I type make, I did have a DD right there, data double. So when you type make, this isn't actually using like a traditional make file because it doesn't need to be complicated at all. We can see that it's just a couple of lines of code here. So first we have the BAS assembler, pass in a line of source code. I have the strict error checking turned on, and I also turned on the benchmark. I think it's kind of cool to see how fast it is. But this is the thing. Here we have checksum64, which is another tool, and this is in the BAS bin folder right there. And so what this is going to do is it's going to do, I believe it is, if not, it's easy to think of it as a CRC check. Yeah, here the value is called CRC. So it's going to go look at, I believe it's the first 4K in the ROM, and generate a CRC code and write it into those values in the ROM header. That's all it does. Very simple little utility, but we really kind of need it. It's not something we know at compile time, and so we have to do it after we've created the ROM. So there again, just filler text. This one ends up, DD is 8 bytes, whereas the DW is 4 bytes. And here we have DB, and again, it's a string, supports up to 27 characters there. And so it can be anything you want as long as it is truly that long. So not a big deal. And then here, device ID and cart ID, and these are not critical values, and here the zeros aren't terribly important either. It's nice to have them right, but 0 is 0. 2 of them doesn't make it any more 0. All right, and so that is our header portion. And then now those were the 2 includes, and so those take the files as source files, and it kind of makes it one great big source file, and then it runs the compiler over it. So it goes and it reads and it finds an include, inserts all of that source code at that point, and then goes and gets the next file and the next file, and so it builds out until it has this huge string file, and then runs the actual compiler over that file. So the insert is a little bit different. This instruction takes a byte, takes this file, N64 bootcode bin, which we have in our lib right there, a 4 kilobyte file, and takes it byte by byte and writes it to the output ROM. So there's a little interesting distinction here. So, and this is kind of what I was calling out on my page here regarding the conventions as far as what each file does and has and such. The N64 include file does not, those instructions don't get written to the ROM unless they are used. And that's because they are of type macro and type constant. So those are only written to the file if and when they are used. And we'll see some examples. I'll show you how that plays out. Whereas this is an ASM file, and this is actual data bytes. So this is written directly to the ROM as you see it. So that's kind of an interesting distinction. So, yeah. I'm kind of want to get a hex editor so you guys can see what happens as these things get put into the output file. And I may do that for the next lesson or so here. So this file only includes what is used and where it is used. This file is data bytes, so it writes out exactly where it's at, writes that data out. And then the insert statement also writes that data out exactly where it is inserted. So first it lays down the header, then the boot code, and then down into the rest of the code. And in the rest of the code, if it's used, it'll be pulled out of the include file. So we'll see some examples. And those, so here, this is a label. And as we saw in this case, the start is tied into the header value. And then down here, we have a loop label, and this is a jump instruction, so it just loops. Infinite loop, just like this while statement here. I really want to focus on each instruction in its own thing, and so I am going to stop now. I think I've covered the basic Bass assembler instructions. And again, once you've written these, odds are you're not going to really change them. If you were doing patches, maybe you would change the origin quite a bit, but that's not the way we'll be using it. So I want to do the Bass specific piece now, and then, as I said, I'll start on some assembly language instructions for next time. Any questions in the chat? All right, seems kind of quiet. I'm going to, well, actually, you know what? I'm sorry. I've got a few minutes here. I will go ahead and make it, and I'm going to debug this so you can kind of see at least the start of the steps of what we'll be doing here. So debug lesson 2. And MAME is, for those that saw in the last session, when you just let MAME run at full speed, it is really, it uses up the whole CPU. When you're running in debug mode, you don't have those kinds of issues. So it's not a big deal. And we'll be doing probably more on the debug side than on the just letting it run. All right, so we started a debug session. This is with our lesson 2 ROM, and we can see right here that it's the lesson 2 ROM. It shows its name here. And remember, we downloaded the ROM file, or the BIOS, N64 BIOS. And so that's actually the code that is in this display right here. So down here at the very bottom line, it's a little bit of a command line. And the best thing I can tell you is help. And so you can see these are the topics underneath help. So what I want to do is I want to get to our code that's actually executing. And so what I want to do is I want to set breakpoints. So I'm going to say help breakpoints. And we can see here BP or BP set, and then the address for the breakpoint. Now, if we go back to our source code file, I'll show you that I'm not just making up numbers here. This is in N64 memory is where our code is going to be at. But as I said, it's going to lay down these header values, and our boot code. So we actually will have this here. I'm going to put it in commented, but just so that it makes a little bit of sense, this is where our actual instructions are going to start. So what I'm going to do is first I'm going to set a breakpoint here so that we can see what is there. And then once again, because I know the values that I want, I'm going to do the same thing with this one. And what we do then is we can go up on the debug menu, and you can see the keyboard shortcuts, which I prefer to use, but I want you to know where I'm finding them. I'm going to run, and so that will run until the next breakpoint. And so there we go. And it goes very quickly. And so this, it looks like assembly language, but it's not. So what we're going to do is, instead of looking at, so this is called the disassembly window on the right side. So instead of a disassembly window, we're going to look at it at the memory window. And we're going to look at 1, 2, 3, 4 zeros. That is not our code. But that is where it starts. So just to pull up what's going on, we can see the LUI statement there. Instead of pif base, it's got this value BFC, and then the add I puts in the value 8 into the T0 register, so that's good. And then we can see the store word instruction is right there. And I'm just going to point out that the labels don't have a line of code. So sometimes those kinds of things aren't always obvious. But here we can see that the loop, jump to loop, we look at this jump instruction, and we can actually see that this label, or this memory address, is the same as where the jump instruction is. So it literally just comes back to itself, which is the way this code is written. Just loop on itself. So I'm just going to step through. I'm hitting F10 to step over. If you were doing a jump instruction or some of the other, there's several other jump instructions, but if you're doing one of those, you can do step into, and it will go to that other section of code. Whereas step over, it might take an extra moment on the jump instructions, but it's just going to go execute that code in the background. And so I'm just going to do the F10 to step. And now we see that it's just going back and forth on this jump instruction. There's a concept at play here called a delay slot. Once again, a big topic we'll cover in much more detail in the future. But our code is running, and that was all I needed to see. Thank you for your time. Give it another chance for questions, and we will call it good. All right, looks like we have some more mega silence there. All right, thank you everybody, and I'll post mostly on the Discord, where so that you can catch me the next time I'm on. Thank you.